Here we're about to have a lot of trigonometric integrals. You guys are going to absolutely love this section, man. Before we get started on some examples, I would like you to just kind of pause this and get some of this stuff down. But I got a few things on here that I hope will help us out throughout this section here. This list right here, calling that the primary list, you're supposed to know how to integrate every single one of those just going straight to the answer, right? You got your reverse derivatives there. You know how to integrate any single trig function. And then right here is the secondary list, is if you have like sine raised to any power or cosine raised to any power, and you pair that with a single sine or cosine, that's just going to be a simple u du, right? So like if you take this example, you can let u equal a single power of that sine function. The du is going to give you that cosine, so you're going to get that other single trig function to match up, and then you have a simple u du right there, right? If you have a tangent to the 80th power or a cotangent to the 80th power, if you got that pair with a secant squared or a cosecant squared, that's, that's something that's going to be a simple u du, because derivative of tangent secant squared, derivative of cotangent is negative cosecant squared. And so anything that's kind of modeling that is going to be an easy u du. There is easy u du in this section, but what we're going to learn this section now, what happens if I got a sine to the 80th and I got a cosine cubed? Right? And so you got these different things that we're going to throw at you. We're going to learn some different techniques in this section, but you always want to try that UDU first. So it's kind of important to recognize what you can integrate and what you can integrate easily, because if you recognize that, then you don't have to go to some crazier technique, all right? The Pythagorean identities, we got to make sure we really know these like the back of our hand, right? So make sure we got those down and variations of those. These even identities, I'm going to prove to you where those come from in a little bit, and I'll refer to those when we're going to use those in a little bit, but hold off on that right now. But there's some helpful things right there. So as we go to our actual notes and our actual examples, okay, with these trig integrals, very important. I want to stress, I'm not going to be completely thorough with these notes. I'm going to be thorough to the extent I'm going to give you the tools that you need for this assignment, right? But I'm purposely going to hold back on some of the problems just because I want to see if you could apply those tools to other looking problems on there. So I don't have a bunch of the tangent cube secant to the fifth on here. I want you to see if you could apply the tools I'm going to give you on these examples to those other examples. And I'll give you a couple what if scenarios, and then we'll of course, we'll ask questions like you always do, and you can let me know if you got questions over things. But one technique that we're going to use quite a bit, and you're going to hear me say quite a bit when we're going through this stuff and we're going through homework problems, is if you have an odd power, chances are you're going to choose that odd power, and you're going to do this thing where I'm going to constantly say save one, convert the other. So you're going to save one of them, convert the other. And when we convert the other, I'm talking about using the Pythagorean identities that we just mentioned there. So here's how the process is going to work, right? You have an odd power. I want you to kind of rewrite this. We're going to rewrite this as sine squared. And I want you to save one of those, that single sine of x. I want you to convert the other one using the Pythagorean identities there. So I think we all know that sine squared is equivalent to 1 minus cosine squared. And then after that, you're going to just distribute and clear out the parentheses. Now at this point, you hope to have something that you can integrate. Sometimes you're going to do a single integral and it'll be like a single u du. This one here, it's actually two separate integrals because I can integrate sine just straight up. And then this second integral right here, I'm going to need to do a u du one. Okay, so sometimes you're going to need to do like two separate integrals. And I think we know then when we integrate, the sine, that's just going to give us a negative cosine. And then right here, I'm going to do a u du. And so I'm going to let the u equal a single power of that cosine. And then derivative of cosine is a negative sine. And notice what you're getting matched up. You got sine of x right there, sine of x right there. So two ways you could think of this. You could think, hey, I got that negative sine of x, and then negative sine of x matches up. Or if you carry down the negative, and then you get the sign to match up, and then you balance it with that negative, then it's going to become a positive right there. And then you have the integral of u squared du. Remember, the squiggle stuff is matched up. Your u is equal to a single one of those cosines, and now you have the integral of u squared. And we know when we integrate that, we're going to get a u cubed over 3. And now we can just plug the x's back in. And then we're done. And then make sure I'm going to link a separate answer key for this section because the back of the book does some very weird things. So we are allowed to stop right there. You don't have to get a common denominator or one single fraction. You can just stop right there and then we're done there. So use that separate answer sheet that I have linked there for you. All right, so let's do another example there. So if you have a choice between an even power and an odd power, I want you to choose the odd power and do this technique where we save one, convert the other. So I want you to choose that odd power, and I'm going to rewrite that as cosine x, cosine squared x. And I want you to save one, convert the other. So we're going to save the one, and we're going to convert the other using the Pythagorean identity. So cosine squared is 1 minus sine squared. And if you have extra stuff, like see how you have this extra sine squared, don't want to change that, all right? You're just going to carry that down. If you have the extra stuff, just leave that alone. Just carry that down. Have that be part of the problem. You don't want to change that to 1 minus cosine squared, okay? We'll talk about why in a second, but you just want to kind of leave that alone, carry that down right there. And then after you do that, you're going to just go to this step and you're going to clear out the parentheses like we did on the last example. So when I clear out the parentheses, some of you, it might help you to rewrite that sine squared in front. Sometimes people make silly mistakes when they're distributing stuff through. I'm going to see a cosine and a sine squared in front of that parenthesis. I'm going to distribute through that parenthesis. So if you want to write it like that, you can, but you don't have to. But if I take cosine sine squared times 1, we get cosine sine squared. And then I have minus, and I go cosine sine squared times another sine squared. So that's going to become a cosine sine to the 4th. Now on this one, I don't have to do 2 separate integrals like we did here. I can actually just do one single u to u that works for both of these, all right? Now, you don't want to let the u equal cosine because the derivative of cosine is a negative sign. You're not going to get a sine squared. You're not going to get a sine to the 4th matched up. And that's why, and so, but what I can do now, I can let the u equal a single power of that sine of x. And then when I do the derivative of sine of x, I'm going to get that cosine of x to match up, right? So I have that cosine of x squiggling out, have that cosine of x squiggling out. So now what I have there, now if I do have a negative in front, I'll just put a negative in front of that whole integral and balance it that way. And then I can distribute that at the end. But I got that to match up. And so your u is one of those signs. And so now what you have to integrate is a u squared minus a u to the 4th. All right, and then we have an easy integral here. So we'll get u cubed over 3 minus u to the 5th over 5. And then I'll plug my x's back in. And remember, we're allowed to just completely stop right there. You don't need to get a common denominator, one single fraction. You don't do anything in factoring or anything like that. Just go ahead and stop right there. That's perfectly good enough answer. And then going back to here, you don't want to, I said leave that sine squared alone. I said just work with the odd power. Choose one, save one, convert the, choose the odd power, save one, convert the other, and then carry the other stuff down. You don't want to change that sine squared and make that a 1 minus cosine squared, because then you're just going to have a bunch of combination stuff right there. You don't really care how high that power of sine squared is. Like even if that was a sine to the 20th power, I carry that down, and that's going to be 20 plus 2. That's going to be a 22 right there. Instead of a 4, you got a u to the 22nd. So that's why it doesn't really matter how high that exponent gets, because if what all you're trying to do here is to try to turn it into something on this secondary list, where if you have a higher power of sine, but you're pairing that with the cosine, that's why we say save one, convert the other, because you're trying to just match up the higher powers of the sines with that single power of that cosine, and that's why that works right there. You're just trying to turn it into, that secondary list there. So what I want you to try to do as well, if you see tangent cube, secant to the 5th, things like that, try that same technique where you save one, convert the other, and then if you got to convert the tangent and the cotangents and stuff like that, then you're going to be using those other Pythagorean identities. So I'm purposely not showing that to you, seeing if you could apply those same tools to those harder looking problems, just with the different trig functions that are in there. You might be wondering, what if you have 2 odd powers? Which one should I choose? What you really want to do is you want to always choose that smaller one. If you have a choice between like a 3 and a 5, choose that 3 and then do that cosine squared right there. You imagine if this was a sine to the 5th, and it would be pretty much the same exact steps, except that would be a 5 there, that would be a 5 there, that would be a 7 there, but it's going to be about the same amount of work there. You want to choose the smaller one if possible. So I'm not going to work through this whole entire problem. I just want to get you started on it, let you know what you're going to run into, right? So I would choose that smaller odd problem. and I would make that like cosine to the fourth. All right. Notice it didn't say save two, change the other. Right? I'm not going to make that cosine squared, cosine cubed. It says save one, convert the other stuff. So I'm going to save that cosine of x. I'm also going to realize that cosine to the fourth is the same thing as cosine squared squared, right? So I can rewrite this as cosine of x, and then convert that other stuff there. I would make that 1 minus sine squared, and then that sine to the seventh would just carry down. I don't really care about that other part of that right there. But here's what you're going to run into. Sometimes these get a little bit lengthy. You're going to need to multiply that out, all right? Because once you do that, save one, convert the other stuff using the Pythagorean identities, your next job is to clear out the parentheses like we did here, except now you're going to have to like have a binomial, write that binomial times a binomial, distribute all that stuff out, distribute the cosine of the sine to the seventh, and then after that point, that's really the hardest part of the problem, because after that point, you might have a few extra terms in there, but it's going to be most likely something pretty easy to integrate just like this. So all these problems are going to look like they're more involved. Like if you just open it up to that assignment, you see nothing but all those trig integrals, that looks pretty darn intimidating. But hopefully if we give you a couple techniques to try here, that's the goal of these notes here. Just give you some tools to try, and then we'll ask questions as we're working through it. So something like that, you can kind of finish up on your own, but you're going to run into stuff like that in the homework. Now you might be wondering, we said if you see an odd power, choose that, save one, convert the other. If you have a choice between odd and even, choose that odd power, save one, convert the other. If you have two odd powers, we said it's going to be like, you choose that smaller one. I guess if they're both threes and they're both fives, it depends on the trig functions that are in there. You just want to choose one and go with it. I can't guarantee that that's going to work. So if I have like a tangent cubed, secant cubed, one of those is going to work, one of those is not going to work, most likely. So you just pick one and go with it. If it works out, if you get to something that you can integrate after you multiply it all out, you chose correctly. If not, you got to go back and just kind of choose that other one. So we'll talk about some of those things as we're going through some of the homework questions. But you might be wondering, what if I don't have any odd powers? So if you don't have any odd powers in your integral, that means you're not going to do that save one, convert the other stuff, because there are no odd powers to work with that stuff there. So if you only have even exponents in that problem, that brings me to these even identities. That's the only time I'm going to use the even identities. If I only have even powers of that sine and cosine, that's when I jump to that even identity. Right here, I didn't only have even powers of the sine and cosine. I had that odd power. So if you see that odd power, make sure you do that technique. Do not use the even identities on this problem when you have that odd power. Now, if that was a cosine to the fourth sine squared, well, then I'm going to think about using those even identities. That's when I'm going to use those if you have only even powers of the sine and cosine. Each year, people will try to use those when they shouldn't be using those, and it doesn't work out, right? So only use those when there's only even powers of the sine and cosine there. If you're interested where these formulas come from, they are an extension of your double angle formulas that you proved last year. So I got that for you right here in case you're interested, okay? Your double angle formula for the like sine of 2x is like 2 sine cosine, right? For the cosine of 2a, that double angle formula that you worked with last year in pre-cal, that was cosine squared minus sine squared. So if we start with the double angle formula that you proved last year, and we're just manipulate that a little bit, right? So let me just kind of talk through it. So what I did, I moved this sine squared over, and then I moved this cosine of 2 over to get this step. And I use my Pythagorean identities, that cosine squared is 1 minus sine squared. And I had a sine squared on each side of that equation. So I'm going to combine like terms. I move that sine squared over there. And then so now I've just got the 1 minus cosine 2a. Now if I divide both sides by 2, I have an identity for that sine squared. Same thing, similar thing here. You can fast forward if you don't care about this stuff there. But if you solve this for cosine squared, I just added the sine squared to both sides. And then the sine squared was 1 minus cosine squared. And I added that cosine squared to that side to make the 2 cosine squared. Then what I was left with over there was 1 plus that cosine of 2a, divide both sides by 2. And now I have something what that cosine of squared a is equal to, right? And so those two formulas are right there. They're actually pretty darn simple to remember because one's a minus, one's a plus, right? So you get that down, no problem. And the way this is going to work, like if you have like sine squared of 15x, right? That's going to be 1 minus cosine of 30x all over 2. That's how that works there. So if you have sine squared of an a, that's going to be 1 minus cosine of 2 times that a, all divided by 2. So the thing is, when it looks like this, we can't integrate it when it looks like that. Now this problem, make sure you pay attention here because this problem pairs all throughout that homework assignment, like several times. So we've got to make sure that we know how to handle that, but we can't integrate it when it looks like that. But if I use the even identities and I turn it into this, look how easy this integral is going to be once I convert it, right? So all I'm going to do now is I'm going to convert that. I'm going to make that 1 minus cosine of 2x over 2. That's the even identity that I just proved to you. And then I can pull out the 1/2. I have the integral of 1 minus cosine of 2x. And now I have like two separate integrals here. I'm just going to integrate that separately. So I integrate one, I get an x. When I integrate that cosine, you're going to get the sine of that angle because the derivative sign is cosine. But remember, your u is equal to 2x, your du is equal to 2. So we'll balance that with a 1/2. And then this 1/2 carries down in front. And what I want us to do for this section, I want us to always clear out the parentheses so we make sure we're all getting the same answer. And that'll help me out when we're doing that testing situation. So always distribute. We're going to distribute that 1/2 right there. Now I'm going to remember the plus C, and I'm going to be done. And that guy pops up quite a bit throughout that homework assignment, so just keep on practicing that there. And then you got to use your brain, right? So like if I were to squeeze, so we're done with that problem, but if I were to squeeze in an X right here, if I put an X in front of that, you know how to do that. All right, so you got to just use your brain to kind of challenge yourself there on some of the harder looking problems in that assignment. That's like a normal thing times a weirder thing. That looks like an integration by parts problem. I can actually use my shortcut, my tabular method on that problem. I can actually go like, hey, my u is that x, that dv is that sine squared, where I could take this derivative down to 0 and I can alternate those signs. And then when you go to integrate this, you just can't go straight to the answer and integrate that very quickly. But you could use integration by parts. You can use your shortcut on that. And when you integrate the sine squared, basically I would just go over there to the side and I would integrate sine squared. At this point, I would do all this work here. I'd do the even identity to get this, and then I can insert that right there. And then I would have a couple easy integrals to do right here. And then I can do that times that times that, right? So that's what I mean. We'll throw a few tricky things at you in the homework, but I'm giving you all the tools in order to kind of figure these things out. All right, so I wanted to kind of mention that, and I mentioned that there. And a couple other things that I wanted to just give you a couple what if scenarios on. That if you have both of the problems are the even identities, then what you're going to do is you're actually going to need to use both of the even identities. All right. Now, what I want to do, I just want to get you started on this one. I think you might have this maybe as a homework problem. I don't want to do the whole thing for you, but I just want to get you started on it. So if you use the even identity for the sine squared, that would be 1 minus cosine of 2x over 2. And if you use the even identity for the cosine squared, that would be 1 plus cosine of 2x over 2, right? So you convert those both. And again, I'm using that because I don't have the odd power in there to do that, say one, convert the other stuff. And so then I would pull out a 1 to the, or 1/4. And I would multiply 1 minus cosine times 1 plus cosine. So that would give me like a 1 minus cosine squared of that 2x. All right, now as you look at this right here, check this guy out. You could integrate this and then integrate this separately, all right? What you probably realize is, man, I have an integral of that cosine squared. I can't integrate that unless I use the even identity. So that means I got to use the even identity again, all right? So some of these problems get a little bit lengthy, but to me, they're a little bit fun, you know, because I'm giving you some tips and stuff to kind of watch for. You got all these tools to kind of use on these things. What you might see right here is what you could do to make that a little bit nicer. Instead of having x minus another even identity, you could actually use your Pythagorean identities there, and you can go 1 minus cosine squared as a sine squared of that 2x, right? And then you still got to use the even identity again. So you would carry down that 1/4, and then the sine squared of 2x, when you use the even identity again, that's going to become a 1 minus cosine of 2 times that. So that'd be like a 4x over 2. You could pull out the 2, have a 1/8 right there, and then you have an easy integral there. So there's something that you can kind of think of there. But you will run into some things where you need to multiply out. So I just ask that you be persistent with that and keep working that in there. Now you will see plenty of stuff with odd exponents, with the tangents and the secants and the cosecants and the cotangents. And I just want you to keep doing that stuff where you have to do that save one, convert the other. And there's another little thing that comes in there. It's kind of like what I call like a hidden UDU in there, where you see some stuff in the match up there. Well, you know, I just want to see if you can figure it out in your homework there. But one technique that pops up quite a bit is like if you have like a secant to the 4th, you might have a secant to the 4th with like a tangent to the 15th power or something like that, or you just got the integral secant to the 4th. But see, the thing is here, You don't necessarily want on this one to make that secant cubed or something like that, because if you have the secondary list, if you could work in a secant squared with any power of tangent, that's a good thing because that's going to be a simple UDU. So what I suggest, if you got a secant squared of 4x, or like just secant to the fourth of x or something like that, what I suggest, if you have a secant to the fourth, make that like secant squared. All right. And then what I want you to do is keep one of the secant squares. I want you to keep one of the secant squares. You don't want nothing but secants in there and nothing but tangents in there because you're not going to be able to integrate that. But if you keep one of the secant squares and then convert the other stuff to anything with tangents in it, that's going to be good, right? So if you have a cosecant to the fourth, you can make it cosecant squared, cosecant squared. If you keep a cosecant squared in there and then convert it to some other powers of the cotangent, that's going to eventually turn into a UDU. So that's the kind of things that I want kind of floating through your head as you're trying some of those things, right? So I would make that secant squared, and then using your Pythagorean identity, the secant squared is equivalent to tangent squared plus 1, right? And then you could like distribute that. You get the secant squared, tangent squared in there, plus this secant squared. And then this was another one like that first example you did. You would have to do two integrals here because you could integrate secant squared straight up. That's going to be a tangent because the derivative tangent is secant squared. And this right here, let your u equal a single power of the tangent because the derivative tangent is secant squared, and you'll get that to match up, right? And so that's why even if you kind of compare that like with the tangent to the 80th power right there, that you would just carry that down, and then this would be like a tangent to the, what, that would be a 2, and then the 80, that would be like an 82 right there. And then you have like a tangent to the 80th in here, and then that would be a single UDU. You let u go a single power of that tangent, and then the derivative tangent would get you that secant squared to match up. So like it doesn't, you know, it might look more complicated, but that concept is the same. And then you got like a u to the 82 plus a u to the 80th power there, right? So just think about some of those things. But like I said, you will see some stuff with the odd powers as well, where you want to pick one, you know, pick that tangent cube, make that tangent squared, use your Pythagorean identity. So you got the odd power technique to worry about, where you save one, convert the other, and that can be applied to sines, cosines, and tangents, secants, and cosecants. So you got the odd power as one of your big tools. And then you also have like, hey, let me write that as like secant squared as a tool. And then you also have your even identities as another tool right there. So we'll throw a bunch of different things at you and just see what you could handle. And then, you know, so I think it's kind of intimidating when you first look at it, but that's all I'm trying to do is give you some tips and some things to think about at the beginning of problems. Extremely important in this entire chapter that you make sure you study the beginnings of these integrals and what those first couple steps are. You got to get that brain recognition down of what to try at the beginning, because if you can't get started at the beginning, then we can't give you any sort of partial credit right there. So please do a great job. One, practice tons of problems where you get the nuts and bolts down. And then also, please make sure you study the beginnings of all these problems so we get that stuff down. The last thing I want to mention, I might mention this in the homework as well, just if you want a challenge problem, if you're doing all these problems and you feel like you're kind of liking them a little bit there, what I want you to do is just try to do this problem with techniques that you've kind of learned either in the past or in this chapter right here. What I want you to do, don't cheat yourself. I want you to use your brain and only your brain, all right? Try that, be persistent with it. Try some things that we've learned this chapter. It might not be this section, it could be a prior section or a prior chapter, but try some things that we have learned. Don't try to like look this up online or anything like that. Just try that with your brain and only your brain, and you'll be pumped up and you'll be pretty happy with yourself if you could somehow figure out the technique that you can use on that. And then when, you know, maybe we'll talk about that at some point in the future there, but I just want to challenge some of my smartest students to see if y'all can figure that stuff out there.